Hi everyone, I'm Grant Weldon. I'm a grad student at UCLA working on dynamics with Smadar Naus and Brad Hansen. And today I'm excited to tell you about a new analytical model we have to describe the orbits of stars in supermassive black hole binaries, potentially being driven to be tidal disruption events, and in particular partial and repeated tidal disruption events. So just as some motivation, there have been many recent observations of repeated tidal disruption events. We learned of several new ones this week. In each of these cases, there's a star on a generally short period orbit, so hundreds of days to a few years, and it gets partially disrupted. It grazes the tidal radius, loses some mass, and then returns for subsequent partial disruptions. But it's challenging to explain how stars theoretically end up on these short period grazing orbits. Traditionally, two-body relaxation is thought to drive stars onto radial orbits to be tidally disrupted, but it's difficult to get these short period repeaters, and so there's some piece of dynamics that's missing. And so one suggestion that's been put forth is that a binary supermassive black hole companion may naturally produce these grazing orbits via the eccentric Kozai-Leadov mechanism, or EKL. I'll leave it to Denise Melchor tomorrow to talk more about interesting things like rates. But today I'll be talking about how this mechanism actually works to drive stars to be tidally disrupted, as well as our new analytical models that might be useful for studying TDEs. I also want to mention that there's been a lot of work lately on secular dynamics. So secular meaning occurring over timescales longer than orbital periods in supermassive black hole binaries. This may produce a burst-like TDE rate. The presence of the companion may alter the trajectories of debris streams post-disruption and create varied morphology in the light curves. You can get off-nuclear TDEs because EKL tends to dominate around the smaller supermassive black hole. That's where it becomes stronger than general relativistic precession. And so you can get TDEs around the smaller supermassive black hole. And then there's been recent work on extreme mass ratio in spiral events as well in supermassive black hole binaries due to EKL. So I'll explain how EKL works. So EKL acts in hierarchical triple systems. So these are systems in which you have a tight inner binary. Here, that's the smaller supermassive black hole and a star in orbit around it, orbited by a distant perturber, in this case, a more massive supermassive black hole. What happens is the inner orbit will undergo oscillations of eccentricity and inclination. You can have very, very extreme eccentricities, and the inclination can even flip from prograde to retrograde. I'll define a few things here. So here I've shown the angular momentum vectors of the two orbits. You can see they're perpendicular to the planes of the orbits. And then I've defined the inclination, the mutual inclination I, to be the angle between these. And then I'm also showing the total angular momentum vector, which we define the z-axis to be parallel to this, and I'll reference this diagram a few times. Here I'm going to show an animation of how EKL actually drives a star to be tidally disrupted. I'm going to describe the three panels before I run the animation. So on the left is the stellar orbit. So this is the star around the smaller supermassive black hole, and in this simulation, the companion supermassive black hole is 20 times further away, so it's way off the screen. And here I'm only going to look at the eccentricity effect. So I mentioned that the inclination will oscillate as well, and I'm just going to be looking at the eccentricity here. The middle panel is a zoom in on the region immediately around the supermassive black hole, because we're interested in resolving this region immediately around the tidal radius, around the supermassive black hole. And on the right, I'm plotting 1 minus the eccentricity of the inner orbit. This is proportional to the pericenter distance. Okay, so I'm going to run this animation. And so you can see that the orbit undergoes these large oscillations of eccentricity. Each time that it comes in, I'm leaving an x at the point of closest approach. And you can see that these points that I've marked with x get progressively closer to the black hole with each oscillation. So there will be a few more here, and then what I'm going to do is I'm going to zoom in even further to better resolve the region immediately around the tidal radius on the next oscillation. Here we go. So in the middle panel, we're going even closer to the tidal radius. You can see that the eccentricity is evolving over a few orders of magnitude. And finally, we have a tidal disruption event. And so these points that I've marked with X are what I'm particularly interested in modeling, because these are the points that represent the overall inward evolution of the star from a large distance down to the tidal radius. If you understand these, you can understand the general evolution of the star. Okay. So just to introduce a tad bit more of dynamics jargon, so here I'm showing some of these cycles. So these are those large-scale cycles of the orbit that we saw in the left panel. Here they're not evolving because the outer companion, so the distant supermassive black hole that's way off the screen, is on a circular orbit, so 0 eccentricity. And these cycles are governed at the quadrupole level in the secular Hamiltonian. So if I say quadrupole cycles, I'm talking about these large-scale eccentricity oscillations. But when you crank up the eccentricity of the outer orbit, the octupole term becomes important, and this drives what we call the secular descent. So it drives the eccentricity to reach even more extreme values, and the star can go down to the tidal radius. And then the final thing I'll define is Jz. So Jz is the z component of the inner orbit's angular momentum. So I showed that diagram with the z-axis, so it's the component of that on the z-axis. And Jz is really important because it controls the envelope of these oscillations. It controls those points that I marked with X in the animation. And so for the circular outer orbit case, you can see that Jz is a constant. But when the outer orbit is eccentric, it can drive Jz to evolve in this stepwise fashion. Okay, so with all that established, we're interested in an analytical model for the time scale in the form of the secular descent, given the orbital configuration of the system. So given the supermassive black hole masses, the separation, the distance of the star, the inclination, the eccentricities, how does the eccentricity of the inner orbit evolve over time? And so this brings us to our first model. So this is an analytical approximation to the stepwise evolution of Jz. I said Jz controls the envelope of the oscillations. This works in the limit of small Jz. So this is systems that are nearly perpendicular, but that's good because this is for systems that are approaching the tidal radius. As the eccentricity goes to extreme values, the inclination tends towards 90 degrees. It tends towards getting a flip in the inclination. And so this system works well for understanding, or this model works well for systems near to the tidal radius. On the left, you can see we're modeling one step in Jz. So on the x-axis, it's going back and forth between low and high eccentricity. These are just those cycles flipped on their side. And we model the step in Jz over one of these 1/2 cycle. And then we can model the step back from high to low eccentricity, and we can keep doing that over and over. And when we piece all of those together, we get the plot on the right. So this is a comparison of the numerical evolution to the analytical approximation. And you can see at large scales, it agrees quite well within a small factor. This model is useful because you can use it to assess the strength of a tidal disruption event. There's this parameter we've seen, beta, the penetration factor, which quantifies the strength of the disruption. So a higher beta is a stronger disruption. And here is an example plot of just for a 10 to the 7 solar mass black hole orbited by a 3 times 10 to the 7 solar mass black hole. Here is the evolution of the star according to our model. And you can use this to see how strong the tidal disruption event is. And in general, EKL tends to produce weaker tidal disruption events or partial tidal disruptions because the changes in eccentricity tend to be very low. So by the time it reaches the tidal radius, it will undergo just a small eccentricity change and be partially disrupted. The second model I want to show is a semi-analytical approximation to the full secular descent. So now we're not taking a look at the stepwise evolution. We're just interested in the envelope of these oscillations. And this is for a larger range of systems. So this is for systems with initial mutual inclinations greater than or about 45 degrees. This is the regime in which EKL can cause these dramatic eccentricity oscillations. And so you can see the comparison between our approximation, which is this grayish shaded region, and the blue curve, which is the numerical evolution. And the shaded region essentially represents a free parameter in the model, varying evolutions of that parameter that we fit to Monte Carlo simulations. This model is generally good to within a small factor for much of the parameter space. So in this plot on the left, I'm plotting on the x-axis this parameter epsilon. So epsilon is the strength of the octopole term. So it depends on the semi-major axis ratio and the eccentricity of the outer orbit. But basically, if you have a higher epsilon, the perturbations from the distant companion are stronger. You have a stronger secular descent. And then on the y-axis is the initial inclination, which is the other important parameter. And so we've sort of mapped out this parameter space. And I've marked with X systems that didn't undergo a flip in inclination, which, as I mentioned, is associated with a very high eccentricity. So you can think of systems with X as systems that weren't tidally disrupted. And then the circles are systems that did flip, so systems that likely underwent a tidal disruption. This red curve is an analytical curve from a paper by Katz et al. 2011. And basically, this, for some region of the parameter space, separates out nicely systems that don't flip from systems that do. But you can see we go down and encompass the entire EKL regime down to about 45 degrees. And the color code in this plot shows the comparison between the numerical evolution and our analytical model. And you can see for most systems, it's good to within a factor of about 25%, and for all systems within a factor of a few. Here, I just want to show some illustrative examples of calculating timescales with our model. So on this plot, on the x-axis, I'm varying the mass of the perturber for a disruptor. So the primary supermassive black hole is 10 to the 7 solar masses. And then the distant one, I'm varying from 10 to the 6th to 10 to the 8th. I'm plotting some different relevant timescales here. So the dashed line is the quadrupole timescale. So this is the timescale of those individual quadrupole oscillations that I showed. They were in the left panel of that animation. This orange line is the timescale for general relativity to cause precession. So when the quadrupole timescale falls below general relativity, EKL dominates, and you can get these dramatic increases in eccentricity. And for those systems, we have the descent timescale using the model is on the order of hundreds of mega years or lower here. And you can see in this case that EKL dominates around the for the smaller supermassive black hole, because if the perturber mass goes below that, then GR will dominate. So that's why we've been showing this around the smaller supermassive black hole. And then just I want to show another similar plot varying the distance of the star from the supermassive black hole. Again, EKL dominates GR when this quadrupole timescale falls below the GR timescale. And the descent times here are on the order of hundreds of mega years down to tens of kiloyears. And so in general, you can use this model to estimate these timescales for stars to be tidally disrupted in a supermassive black hole binary. You can use it to calculate rates. Denise will show some examples of rates in supermassive black hole binaries tomorrow. I also want to point out that these approximations are also applicable to many other systems in which EKL drives the eccentricity to extreme values. So asteroids, planetary systems. I'm particularly interested in the migration and tidal disruption of hot Jupiters. So if you're interested in that, we can chat. Planets around white dwarfs and neutron stars, stellar mergers, compact object mergers, and many more. So some takeaways are that eccentric Kozai-Lidov in supermassive black hole binaries is a promising formation channel for TDEs, and in particular partial and repeating TDEs. We've derived these novel analytical approximations which can describe the descent of a star from a large distance down to the tidal radius. And you can use these to calculate distributions of penetration factors and rates of tidal disruption in supermassive black hole binaries. Yeah, with that, I'd be happy to take any questions. Thank you.
Please, go ahead.
Thank you for your talk. What is the time scale, like how does the time scale of these AKL oscillations compare with the encounter time scales of the stars with each other? So I am asking if it is shorter or longer, can you effectively bring the star close to the black hole without disrupting its orbit?
Are you talking about like two-body relaxation?
Yeah.
Yeah, so the general like definition of two-body relaxation is like the time scale for the angular momentum to change by like an order of itself, and that tends to be much longer compared to the EKL time scale. But individual kicks can shrink the semi-major axis on relevant time scales, which could potentially lead to these short period repeaters. So yeah, Denise talks a bit more in her talk about combining two-body with EKL.
Thanks.
Yeah, thanks for the great talk. Do you have an estimate of the tidal heating accumulated in this process before it reaches the tidal disruption radius? Because I imagine if you already have like approximation for the JZ, then you should be able to like estimate the total energy. Like, yeah.
Yeah, totally. I haven't looked at that yet, but that'd be really interesting to look at. I think that's one of the next things that we wanted to see. We first wanted to understand the dynamical perturbations that these stars will encounter, but yeah, that'd be interesting to look at.
Yeah, because if you have accumulated a lot of tidal heating, for example, they may actually change your stellar structure and can provide some evidence for, yeah. Like,
sure, totally, so, yeah, that'd be good to look at. Thanks, yeah.
Hi, awesome talk. I was wondering, you focused on eccentricity evolution over time for this talk, but do you have a sense of like the inclination distribution? You kind of mentioned that, you know, in one of your analytical models, it's 90 degrees or so. At the time of tidal disruption, do you have a sense of what the inclination distribution looks like and how that is for repeaters in general?
Yeah, so that's something we want to take a closer look at. So yeah, for some inclination distribution, or for some system that has some inclination, its inclination will oscillate sort of like the eccentricity did, but it will gradually get closer to 90 degrees until you get a flip. So I assume that the inclination distribution will be, it won't be isotropic. It will be somewhat closer to 90 degrees, but that's something we want to look at. And we also want to look at how two-body affects that as well. Yeah,
thanks.
Yeah, great talk, thanks. I'm curious about how you interpret the evolution of the eccentricity after you've hit the tidal disruption radius. So if I understand, it's a partial disruption, so there's still some kind of nugget of star left that's, you know, supposedly circling the black hole, but it seems like it actually gets less eccentric over time and doesn't hit another tidal disruption again, right? So it doesn't come around and get tidal disrupted. So what do you think is happening there?
Yeah, so we haven't really looked at what happens once you get there. We're just trying to get orbits down to, with high eccentricities down to the tidal radius. That is one of the things we want to look at next is actually following the star once you reach down to the tidal radius. But yeah, in general, I think these tend to be weaker disruptions. But yeah, I want to look at that and then track the eccentricity evolution afterwards too. Yeah.
Cool. Thanks.
Hi, great talk, thanks. I was wondering if for this mechanism to work, the triple system needs to be hierarchical and stable. Mm-hmm. So I was wondering, like, how large is your region of the parameter space that you have in mind for this to actually work?
Yeah. So generally, the systems that we're thinking of are when the supermassive black holes are on the order of parsecs, roughly, in separation. And then these stars are fractions of that, like in the nuclear star clusters around these black holes.
Okay, thank you.
Yeah.
Yeah, thanks for a nice talk. Yeah, I really like the animation of the star getting closer, and kind of like a Jaws do moment I had. But I'm curious about whether or not these are very good or better at making partial disruptions compared to just the full last cone, because there you also diffuse in small steps, right? So is it the same, or is there anything else?
Yeah, so I think I think it's really the combination of these that's very strong. You can't really, EKL and two-body will do sort of similar things, but it's really when they're combined, and this is what Denise is doing, because you can essentially diffuse a star into the region where EKL is very strong, and then EKL can, you can do that with two-body, and then EKL can take over and then drive the star down. So I think they really work together to produce a much higher rate than each of these effects alone, if that makes sense.
Oh, so it's a rate enhancement, and then it has to be, then you always get these modest betas.
Yeah, I think so, yeah. Thank you.
So maybe just a comment about this question about tidal heating that was raised. So I think, yeah, in general, once your orbit starts to become quite eccentric and tidal heating becomes to dominate, you might actually end up kind of effectively bringing the tidal radius out towards the star. Now it's the question of how is this process of, you know, the effective change in the stellar structure or the timescale over which it evolves compared to these other processes. So that will determine the ultimate fate and, you know, the process that actually, you know, ends up disrupting the star.
Yeah, that makes sense.
Actually, totally related to this, you would also spin up the star when you get closer without necessarily disrupting it. And this would, again, push out the effective tidal radius.
Mm-hmm.
If there are no more questions, then let's thank the speaker again. So we have now the lunch break, and we'll reconvene at 2 p.m.